Can you change to the next one? Yes. It is a U.S. Department of Energy-led international collaboration. It takes 16 countries, 60 institutes, 600 physicists, 17 years. There's United States, Mexico, Denmark, Netherlands, France, Spain, Portugal, Italy, Switzerland, Germany, Russia, Korea, China, and Taiwan. The detector were built all over the world and assembled in Geneva, Switzerland at CERN. The realization of AMS come from three reasons. One is the strong endorsement of AMS science from reviews by world's leading scientists. The second, as you probably know, this experiment received unanimous support from the United States Senate and House of Representatives. Third, perhaps even more important, is made possible through worldwide support. From United States, there's NASA, there's DOE, also from MIT. And we have strong support from CERN and ESA, from France, from Spain, from Italy. Italy has two major institutes, INFN, the Institute for Nuclear Physics, and ASI, the Italian Space Agency. From Switzerland, there's ETH, that's the equivalent of MIT, maybe better. and then from Geneva. And from Germany, it's from RWTH. That's definitely a better school than MIT. And also the German Space Agency. And then we have very strong support from Taiwan, from Academia Sinica, and from an institute called CSIST, and we also have some involvement from the People's Republic of China, particularly 10 years ago. AMS is a trillion electron volt precision multipurpose particle physics spectrometer. So that itself, it's a simple thing. The difference is you want to put a particle physics detector, a state-of-the-art detector, in space. So you all perhaps remember every particle and nuclei are defined by their nuclear charge and defined by their energy. So the first detector is called TRD. It's measuring electron positrons, followed by time-of-flight counter, measure nuclear charge, which is called Z, and energy. And then we have very, very precise silicon detectors, which measure charge and momentum, and the magnet determine the sign of the charge. We have a ring image Cherenkov counter, otherwise known as RICH, measure charge and energy, and at the bottom is an electromagnetic calorimeter, 648 kilogram, measure electron, positron, and gamma rays. Therefore, all the detectors measure energy and charge in a repetitive way. This is the transition radiation detector, identify electrons and reject protons. This is one of the extremely beautiful, elegant silicon tracker. There are 9 planes, 200,000 channels, and they have this measure things to 1/10 of your hair. This is a ring image Cherenkov counter. It's very precisely made, has 11,000 photosensors, identify nuclei and energy. At the bottom is an electromagnetic calorimeter made out of 50,000 fibers sandwiched in 1,200 pounds of lead. So you can measure extremely high energy gamma rays and electrons and positrons. No other detector in space up to now has this radiation thickness of 17 radiation lengths. So this was AMS-02 when arrived at Kennedy Space Center. So different from previous science on the space station, I will call this fundamental science on the space station. You can understand this very simply by realizing in space there are two types of cosmic rays. One type, light rays. Light rays has no charge, no mass. And in fact, all this beautiful work done at NASA, Kobe, Hubble, and done by European space agencies, Integral and Fermi, and many, many experiments, all measuring light rays. In fact, most of our understanding about cosmos up to now come from measuring of light rays. But besides the light rays, there are charged particles. Because it has charge, you must have a mass. And once you have a mass, then it's absorbed in Earth's atmosphere. So you have to go to space to measure the primary cosmic rays. And because it carries a charge, you need a magnet. Because only in a magnet, positive bends one way, negative bends another way. And so the simplest way to view this detector is light rays has been measured extensively. Many detectors. Charged particle for long duration, precision measurement to trillion electron volt is the first time. In other words, you open the door, enter into a new area. Some of the physics include the origin of dark matter. We know, and you certainly have heard, 90% of the matter in the universe is not observable. And because you cannot see it, that's why you call dark matter. Nobody knows what it is. So on the left side, you see a galaxy seen by a telescope, but that's only 10%. If you can see all the rest, a galaxy will look like on the right side. How do you detect dark matter? In space, we know there are cosmic rays, protons, electrons, helium. Collision of ordinary cosmic rays, of course, produce other particles, such as positrons. Now, to search the origin of dark matter, the collision of dark matter will produce excessive positrons. The existence of characteristic positrons way above what you predicted from ordinary cosmic ray is a unique signal to tell us we have finally understood what are the other 90% of the matter. Another physics example is the search for antimatter in the universe. If the universe begins with the Big Bang, before the Big Bang, there's a vacuum. Nothing exists in vacuum. After the Big Bang, there must have been equal amount of matter and antimatter. Otherwise, you could not have come from a vacuum. AMS on the space station for the lifetime of space station, hopefully, is 20 years. We will search for the existence of antimatter universe to the age of observable universe. about 1,000 megaparsec. If you think about it, it's very strange. If you come from a Big Bang, at the beginning there must be equal amount of matter and antimatter. And the question is, where's the other half? So those are two simple physics examples. Another physics example, which is really the work of Professor Jack Sandweiss of Yale University, is to search for new kind of matter in the universe. You must have heard from accelerator, we know the smallest element in nature are quarks. And there are 6 quarks has been found. But it is very strange. All the matter on Earth, like this glass or this water, are always made with only the first 2 kind of quarks. So the question is, there are 6 quarks that exist in the universe. Why everything on Earth is made out of the only first 2? Are there ones made from the 3rd quark? And this we should be able to search. Now this is a very large international collaboration. The transition radiation detector was made in Germany with the United States, Taiwan, and Italy. The time of flight was Italy, United States, and Taiwan. Magnet is made in Spain, in China, in Germany, in Holland, in Russia, in United States, Switzerland, and Taiwan. So to be a principal investigator for this large experiment, one of the requirements is to know the flags of every country. So I'm very, very pleased and honored today you have a chance, okay, not only to ask me, afterward you have a chance to have an interaction in a formal or informal way with my senior collaborators. From France, there's a Mr. Jean-Pierre Vial, who is there. And from Germany is Herr Professor Dr. Scher from Aachen. And most of the people used to think Aachen is the center of the universe. And we have an enormous amount of contribution from Italy. It's supported by the Institute of Nuclear Physics, INFN, and Italian space agencies. And there are in total 6 universities, 5 sections, and enormous amount of national effort. And this is under the leadership of Roberto Batisson, and who also, besides being a deputy principal investigator of AMS, he also chaired the National Committee on Astroparticle Physics for Italy, deciding space experiment and deciding on ground-based non-accelerator experiments. And then there's Mr. Aguilar, who is visiting and seems to have badging problems, so could not come here. And from Spain. And he's a member of the Royal Spanish Academy of Science. Very, very distinguished physicist. And from Switzerland, we have a very good collaboration from ETH Zurich and from University of Geneva. And for us, this is a unique opportunity to have the French-speaking Swiss and the German-speaking Swiss working together. And this will be done by the former president of University of Geneva, Maurice Bourquin. We have also a very large contribution from Taiwan, and this contribution is mostly in electronics. We have 650 microprocessors, and most of them are made there. And this is done by Professor Li who, again, recently been selected to be member of the Academy of Academic Seneca. So after my presentation, after your question, and you please reserve hard questions to my colleagues. And so people ask you, you have spent close to $2 billion. What are you doing? What are you going to learn? The issue of antimatter in the universe and the origin of dark matter, of course, probes the foundations of modern physics. But to a scientist, the most exciting objective of AMS is to probe the unknown, to search for phenomena which exist in nature that we have not yet imagined nor have the tool to discover. So let me share with you the major discovery in physics over the last half a century. When I first received my doctorate degree, there were two largest accelerators, one in Geneva, one in Brookhaven. The original purpose, the review from members of the National Academy of Science by leading scholars to say these accelerators are very important, you can understand nuclear force. What was discovered was something called neutral current. There are two kinds of neutrinos, breakdown of time reversal symmetry, and new form of matter. Most of these were given Nobel Prizes. United States in 1970 built a 400 billion electron volt Fermi National Laboratory to study neutrino physics, and what was discovered was the fifth type of quark and the sixth type of quark. The Stanford Linear Accelerator in 1970s was to understand the property of electricity. What was discovered are partons, the fourth type of quark, and third kind of electron. The large underground cave in Japan, its original purpose was to look at how long protons live. What was discovered was neutrinos actually has mass. Even Hubble telescope, its original purpose was galactic survey. Among its many discoveries are the flat curvature of the universe and the existence of dark energy. And so for AMS, facing all of you, I have mentioned we can look for dark matter, look for antimatter, look for strangelets. We say this because this is our current knowledge. But advanced physics is to push the current knowledge aside. Then you can move ahead. And so exploring new territory with precision instrument is the key to discovery. What we really would see, nobody knows. I mean, if you find what you predicted, it's not interesting. The interesting thing is to destroy the current idea, to find something new. This is how science advances. So I've finished now, and I'm happy to take questions.
Thank you, Professor Ting. The AMS collaborators that Professor Ting identified will be available at the conclusion of this briefing for your questions. For now, we'd like to limit your questions to those who are on our panel. Please wait for the microphone, state your name and affiliation, and to whom you're addressing questions. We'll start over here with Seth Bornstein.